Hey everyone, in this video we're going to look at how to solve equilibrium problems using a common approximation known as the small x approximation. This is going to be in rice table problems when you have a small k value, and since that's true of most k values that are of interest, in particular in biological situations, this is going to be a really helpful and useful approximation for us. It's also going to help us avoid a ton of algebra, which usually makes everybody happy. Okay, but it does take a little time to get your brain wrapped around it. So let's just work through an example and we'll see how this works. For the reaction below, which I totally made up, calculate the equilibrium concentration of ClO if initially the Cl concentration is 1 molar and the NO2 concentration is 0.4 molar. So we're going to create a rice table, as we've been doing, and we're going to plug in what we know. We know that initially the Cl2 is 1 molar, and initially the NO2 is 0.4 molar. We're not given any values for ClO and N2O2 Cl4, so we assume that those are 0, because if we didn't put any in, there isn't any there to begin with. All right, so now this is going to go towards equilibrium. Notice that there's no products present. They're both concentration is 0. So this reaction has to go forward. But we don't have any, we have no equilibrium values. So we have no way to predict how much or how large the change rho is going to be. And when we don't know what things are in science or math, we call it x, okay? So we know that for Cl2, it's going to go down 3x. It's 3 because the coefficient of the change rho always matches the coefficient of the stoichiometric relationship in the reaction equation. So it's going to go down 2x for NO2, and then it'll go up 2x for ClO, and then up x for N2O2 Cl4. Pay attention to your signs. If this reaction is going forward, both of the reactants have to be positive, both of the products have to be, both of the reactants have to be negative, both of the products have to be positive. We'll deal with reactions that go products to reactants at a later date, but the signs on either side should agree with each other. All right, so now we're just going to add down. Initial plus change adds up to equilibrium. So this is going to be 1.0 minus 3x, 0.40 minus 2x, 2x, x. Okay, so far so good. Now we're going to write an equilibrium expression for this crazy reaction. So this is going to be ClO squared, this monstrosity to the first, over Cl2 cubed times NO2 concentration squared. Now what we're going to do is take this equilibrium rho and we're going to plug it into the equilibrium expression. All right. So that's going to give us, let's see, ClO is 2x squared. N2O2 Cl4 is x over 1.0 minus 3x cubed times 0.40 minus 2x squared. Right? And that's all equal to the equilibrium value, 1.0 times 10 to the minus 6. Now, the goal here is to solve for x, but notice that x is all over the place. So you've got x's in the numerator, you've got x's in the denominator. Those ones in the denominator are a real pain because they're being added and subtracted, and what you would normally have to do is cube this quantity out, square this quantity out. If you remember the FOIL method from algebra, then you'd still have to multiply those two polynomials together, and you end up with fifth order polynomials. It's a huge disaster. So instead, there are ways to plug this into some of the graphing calculators if you have one, but we're going to usually, again, be working with k values that are quite small. Usually if the k value is less than about 1 times 10 to the minus 3, the approximation I'm about to show you works pretty well. So what we're going to do is we're going to say, all right, we are subtracting. So x is going to come out to be a small number because this k value is really small. So if the k value is small and the x value is small, doing 3 times a really small number is still a really small number. And then subtracting it from 1 is going to result in something that's like 0.99995. So in other words, if it goes from 1 down to 0.99995, who cares? We can just ignore these added and subtracted x's, and we're probably not going to change the answer very much. Because they're really little, and they're just going to be overwhelmed in terms of how big they are by being added or subtracted from these bigger numbers over here, okay? So the analogy I always use for this is if you have a bank account and you subtract a penny, someone subtracts a penny from your bank account, if you have $100 and it goes down to $99.99, you may not notice that, right? So those small subtractions aren't going to matter. Now these ones in the numerator up here, these are multiplied. That's a big deal. If you were to if someone took your bank account and multiplied it by 0.01, you would notice that because it would go down really fast, all right? So multiplied x's have to stay around, but these ones that are added and subtracted, we're going to just neglect those, okay? We're not canceling them. Please don't call it canceling. We're neglecting them, all right? And we're going to say they're small enough to ignore. So let's see what that does for us. Well, that gives us, up top, we still have our 2x squared times x. Now in the denominator, we have 1.0 cubed. That's a lot easier to deal with. And we have 0.40 squared. So this is way easier to deal with. No fifth order polynomials, no weird trying to remember how to do that, okay? All right, so now what we're gonna do is we're gonna take, we're gonna solve for x here. What I'm gonna do is I'm gonna cross multiply here, and also I'm gonna simplify. So 2x squared, now be careful here, y'all. A lot of you haven't done this in a while. 2x squared is 4x, oops, is 4x squared. Why? Because the exponent applies both to the 2 and to the x, so be careful. And you've still got another x out here. We'll deal with that in a second. Okay, that's going to be equal to 1.0 cubed, which is just 1, 0.4 squared times 1.0 times 10 to the minus 6. Okay, back over here, you've got 4x squared times x. That's 4x cubed, right? The exponents add. You got a 2 and a 1, that adds up to 3. Over here on the right-hand side, now we're going to break out our trusty calculators. 0.4 squared, don't know where the square button is on this calculator. Oh, well, times 0.4, times 1e minus 6. That gives us 1.6 times 10. Oh, I could have done that one in my head. To the minus 1, 2, 3, 4, 5, 6, 7. Okay, just making sure I did it right. Yep. All right, so now we're going to divide both sides by 4. That gives me x cubed equals 4.0 times 10 to the minus, I think that's still 7. 2, 3, 4. Oops, 8, haha. Just kidding. Of course it is. Dang nabbit, come on. I should have just done that in my head, it'd been faster. Okay, now we're going to take the third root of both sides here. So now you get x equals, now finding the third root button in your calculator is a huge pain. It's much easier instead to raise this to the 1/3 power, all right? That's usually way easier to do in your calculator. When you do it, make sure that you put the 1 divided by 3 in parentheses. So like if you're typing this in as 4.0 times 10 to the minus 8, put that in parentheses, caret, and then parentheses 1 divided by 3. Okay? Even better would be to enter this as 4.0 and the small uppercase e, and then do the caret, 1 divided by 3. But the key thing here is that these parentheses have to be here, or it will not go well. You will cry, okay? Or I will cry, or we'll both cry. So that comes out to be that, right? Now this wasn't the original question. The original question was calculate the equilibrium concentration of ClO. Well, ClO has an equilibrium concentration of 2x. We just found x. So 2x, which is equal to the equilibrium concentration of ClO, is going to be twice that. So that's going to be 0.0068. And that's molar. Okay. Ta-da! Okay, so let's review what we did. You've got to fill out your rice table. Your change row reflects the coefficients of the reaction equation. You're going to write the equilibrium expression plug into the equilibrium expression, neglect x's that are added or subtracted from much larger numbers. This is valid as long as the k value is small. Do a bunch of algebra, get your x value, double check which x value you need for your answer, and then you're done. Okay? This comes with practice. By the time you've been doing this for a week, you'll do it really, really fast, okay? But initially it's going to take some practice. So what I'd like you to do, I've written out a practice problem. I'd like for you to pause the video, get out a pencil, paper, and your calculator, try to do the problem, hit play, and then watch me do it. Okay, here we go, folks. So we're going to make a rice table. We know that initially these over here are 0.1. These initially are 0. This will be minus 4x, minus 3x, plus 4x, plus 2x. So this will be 0.1 minus 4x, 0.1 minus 3x, 4x, 2x. We've got a nice small k value, right? 10 to the minus 8, that's 0.000000047 or 46. So that's quite small. So this small x approximation is going to work here. We're going to do k equals CLO to the fourth. This is another reaction I totally just made up. Okay, I'm 90% certain this doesn't happen in nature. Okay. All right. Now we're going to plug equilibrium rho into equilibrium expression. So that's going to give us 4x to the fourth, 2x squared, over 0.10 minus 4x to the fourth, 0.10 minus 3x to the third. That's all equal to 4.6 times 10 to the minus 8. Okay, so everything's so far so good. We are going to neglect these. And I think it's a good idea to write out the word neglect so you remind yourself what you're doing. All right, so now simplifying, let's simplify the top as well. So 4 to the fourth is 64, x to the fourth times 4x squared over, right? I did that right? 4 to the fourth is 64. No, haha. I'm glad. I knew that didn't sound right. That's 4 to the third. It's 256. There we go. All right, over 0.4 to the fourth is 1.0 times 10 to the minus 4. 0.1 to the third is 1.0 times 10 to the minus 3. And you could even simplify this again before you cross multiply, which might be the better way to do it. So that's going to be 1024x to the sixth over 1.0 times 10 to the minus 7. Okay. What am I doing? Sorry, I'm having calculator problems. Quit. Yeah, okay, good. I was just double checking that last one. I thought I'd done that right in my head, but sometimes scientific notation is with me and sometimes it isn't. All right, so now we're going to cross multiply. So we got 1024x to the sixth equals 4.6 times 10 to the minus 15th power. Divide both sides by 1024. I made up these crazy coefficients so we would get some crazy values in here, and it worked, right? So, okay, then divide by 1024. So we've got x to the sixth equals 4.5 times 10 to the minus 18th, and then we raise both sides to the 1/6 power. You know, there was a time when people had to do this by hand. You can't do this stuff without a calculator. Okay, now that's going to give us that x is equal to 0.0013 molar. All right, that seems like a pretty reasonable number. All right, what was our original question? I've already forgotten. What are the concentration of both reactants? So ClO is 4x. So 4 times that 0.051. And what was our other product? Cl2O is 2x. Okay, so that one's going to be 0.0026, and those are both molar. All right. Okay, this was a quick introduction. It's going to take some practice before you get it down, but don't get frustrated, and feel free to reach out for help. All right, hope this was helpful. See you soon.